How can a helicopter fly on just one rotor blade? This machine was built to shatter almost everything you thought you knew about rotorcraft. A single blade, 50 feet long, spun by a jet of compressed air venting at its tip. But that isn't the strangest part. If it worked, that blade would stop dead in midair, fold flush against the fuselage, and the aircraft would tear off at a speed every helicopter of its era could only dream about. Strap in, because we're about to lift off aboard the strangest helicopter in aviation history, the Sikorsky XV-2. We begin where most aircraft end their story, high in the air, rotor frozen still. Up close, the first thing that stopped you cold was the rotor, 50 feet across, twice the wingspan of the aircraft itself, and carrying exactly one blade. The other side of the hub had no second blade, just a solid slug of aluminum bolted on as a counterweight, like a propeller that had lost its other half. The blade had no engine of its own. All its thrust came from a jet of compressed air venting at the tip, the reaction spinning the whole system around. That air was fed by a Wright GT-43 Typhoon turboprop in the fuselage, 1,050 horsepower, running continuously to keep the pressure up. It never drove the rotor through a shaft. Its only job was to make pressure. Second, no tail rotor. On a conventional helicopter, it's all but mandatory. The engine drives the main rotor through a shaft. The body wants to spin the opposite way, and the tail rotor cancels that torque. But the XV-2 had no engine-driven drive shaft and no torque to cancel, so the tail rotor was redundant. On paper, it all made sense. Where it stopped making sense was the part that had rival convertiplane engineers calling Sikorsky insane. At altitude, the pilot pressed a button. The tip jet faded, the rotor slowed. Not to land, but to stop entirely. 50 feet of metal, moments earlier turning hundreds of times a minute, had to come to rest in midair, fold down, and slide into a bay atop the fuselage. In other words, the helicopter had to shed the one feature that made it a helicopter, thousands of feet up. Meanwhile, short delta wings and a separate jet engine would drive it to 400 knots, nearly twice as fast as any helicopter of the day. That was the whole plan, and nothing in aviation history had ever worked this way. Not before, and not for the 73 years that followed. There was only one exception, and it came very late. In 2021, engineers in Singapore unveiled a machine that flew on a single wing, folding smaller than your fist, and it flew steadily for 16 minutes. The XV-2 itself was never built. To understand why, we have to go back to the moment the helicopter industry ran headlong into an invisible wall. By the late 1940s, the helicopter was no novelty. The Sikorsky R-4 pulled men out of the jungle in Burma. The Bell 47 was flying commercially. But engineers spoke quietly about a number none of them dared promise a customer. 180 knots, about 333 kilometers an hour. That was where physics folded its arms and refused to cooperate. The culprit was a phenomenon called retreating blade stall. A rotor blade moving backward against the direction of flight loses its lift. The faster you fly, the greater the imbalance between the two sides, until the helicopter simply cannot go faster. The Air Force and the Army wanted that wall broken. In early 1950, they opened a convertiplane competition. Aircraft half helicopter, half jet, able to lift off vertically and then fly like a fixed wing. 3 proposals were chosen. The McDonnell XV-1, sensible and conservative. The Bell XV-3, a tilt rotor that swung its rotors forward, the ancestor of the V-22 Osprey, and the Sikorsky XV-2, which nobody in the room truly believed could fly. But the Air Force wanted bold ideas, and the XV-2 was as bold as it got. Sikorsky got the contract. On the drawing board, it looked like it came from another planet, and it broke nearly every rule of its era. No tail rotor, no transmission, no engine-driven drive shaft in the classical sense. One blade balanced by an aluminum counterweight, and short delta wings under a body built to swallow that rotor whole once it stopped. Those delta wings came from a man little known outside the industry, Michael Gluharev, Sikorsky's chief design engineer through the 1940s. A Russian émigré and Igor Sikorsky's closest collaborator. In his spare time, he designed a tailless delta-wing aircraft he called the Dart, building a balsa wood model in 1939. He held 3 delta-wing patents, ideas that ran well ahead of their time. That balsa dart still sits in the Smithsonian today.
But the man who would carry this story further wasn't Michael. It was his son, Eugene Gluharev, who worked in the same building, developing the tip jet system for the XV-2. Eugene had sat at the same table as Igor Sikorsky and his own father while they sketched the first designs. He believed in the tip jet more than anyone in the industry, including, perhaps especially, the people paying him to believe in it. Then, in 1950, just as the Air Force chose the XV-2, Eugene left Sikorsky. He moved to California and joined the American Helicopter Company in Manhattan Beach. Maybe he didn't trust Sikorsky to see it through. Maybe he wanted to prove it himself. Either way, the one-blade idea his family had helped create no longer sat inside a single building. It had 2 paths, and they would run in opposite directions for the next 10 years. Sikorsky needed to know one thing before cutting metal. Could a one-blade rotor survive in real air? The answer had to come from a field test, not a wind tunnel. They took a spare R4 from the shop, a 2-seat helicopter with a conventional 3-blade rotor, stripped away 2 blades, kept 1, and added a counterweight. In August 1948, at Bridgeport, Connecticut, the odd little R4 lifted off. It flew, but there was a problem. Once per revolution, the lone blade produced a pulse of lift, and for the other half of the turn, nothing. The whole helicopter bounced in time with the rotor, a violent, relentless shudder. Sikorsky's internal report noted that the counterbalance proved acceptable, but the aerodynamic vibratory loads were a concern. The counterweight was fine, the vibration was not. From 1951 to 1953, Sikorsky moved the XV-2 into the wind tunnel at Wright Field, Ohio. A 20% scale model first, then a 5% one, then rotor models to measure the loads when the blade stops in midair. This was the hardest part. While the rotor spins, lift is symmetrical. But when it stops in a 200-knot airstream, one side carries lift and the other none, and the aircraft wants to roll at once. The engineers had a plan. Lock the blade's flapping hinge below 25% of design rotor speed, and stop it at the instant lift falls near 0. In theory, it wouldn't roll. But the wind tunnel wouldn't tell them what they wanted to hear. Then, in 1955, something quiet happened inside Sikorsky. The XV-2 design was revised. The single blade was replaced with 2. It could still fold. It still had the tip jet. it was still a convertiplane. But the original idea, one blade and one blade only, had been quietly withdrawn by the very company that created it. No announcement, no press release, just a new drawing replacing the old one in a drafting room drawer. It was the first sign the faith was faltering, not because the idea was wrong, but because even the men who created it were beginning to fear it. By the late 1950s, the program collapsed. Budgets shifted to supersonic bombers and missiles. The XV-2 was canceled before any airframe was cut from metal, and the serial number 54-4403 assigned to it was never stamped onto an aircraft. The McDonnell XV-1 flew a few hundred hours and was abandoned. The Bell XV-3 kept going, slow and difficult, but it moved forward. 3,000 miles west, in California, Eugene Gluharev was solving the same problem by refusing to accept it. He had no wind tunnel, only a small shop and a simple line of logic. If a single blade shakes itself apart at large scale, then make it small. Small enough for a man to wear on his back. In 1952, he founded Gluharev Helicopters Corporation. No military contract, no big office, just him, a few drawings, and a determination that if Sikorsky wouldn't dare, he would. His problem was different from Sikorsky's. He didn't need to convert rotor to wing or stop a blade in midair. He only needed a rotor spinning hard enough to lift one man off the ground. At his scale, dozens of times smaller, the vibrations that worried Sikorsky became something a pilot could manage with his own body. He invented his own pressure jet engine, the G8-2, burning liquid propane at the blade tip. The machine weighed less than 30 kilograms. Somewhere in California, between 1957 and 1959, Eugene Gluharev, 40 years old, the engineer who had once sat at the same table as Igor Sikorsky, strapped the MEG-1X onto his back and lifted himself off the ground. A single blade overhead, a propane pressure jet at its tip. He was the design engineer, the mechanic, the pilot, and the test subject all at once. The machine flew for minutes at a time and reached a ceiling of 1,500 meters. The very idea Sikorsky had abandoned just a few years earlier, Eugene proved worked on his own back. There was one moment in the XV-2 design that no engineer ever solved. The one Eugene had wisely avoided. The blade changing from rotor to wing. Stopping in exactly the right position without rolling the aircraft. Lift and moment balancing almost instantly. It sounds simple. It isn't. The problem wasn't the materials, or the engine, or any single piece of aerodynamics. It lived at the intersection of all of them, where every equation was right on its own, but wrong the moment they sat down together. And every generation that followed believed new technology would finally break it. In 1976, DARPA revived the dream as the X-Wing. Lockheed studied it first. Then, in 1983, Sikorsky converted an S-72 into a test bed. By 1986, the airframe was ready. By 1988, the program was canceled, without a single flight. Computers were now thousands of times more powerful. Composites had replaced aluminum, and still it wasn't enough. Then Boeing tried, more ambitious still, with the X-50A Dragonfly. 2 unmanned prototypes, $51.8 million invested, fly-by-wire, on-board computers. Everything the XV-2 lacked, the X-50A had. Ship 1 crashed on March 23, 2004, on its third flight, from a cross-coupling of rotor controls, the blade and the flight controls fighting each other. Boeing built Ship 2 and fixed the faults they'd found. On April 12, 2006, Ship 2 crashed at Yuma Proving Grounds on its sixth flight of a planned 11. Neither prototype ever transitioned into forward flight. Later that year, DARPA closed the program with a single phrase: inherent design flaws, unfixable.